Hello, and I guess welcome to this video on nodal analysis. So what I want to do in this video is I just want to do an example problem. Really, if you're looking for more instruction on what nodal analysis is and kind of the operations of it and how and kind of what the steps are, you might want to watch one of my previous videos on nodal analysis because really what I'm going to be doing in this video is just kind of going through a problem using nodal analysis. I might not go through every single step in as much detail as I have in other videos. This is really just an example, if you want to see me going through one more problem. So anyway, here's the problem. I am going to have a 10 milliamp current source, and my circuit network is going to look like this. I have a 2K resistor there, a 5K resistor here, and I've got a 13K resistor here. And what I care about in this problem is I care about what is the voltage across this 13K resistor. So anyway, this is the problem. So let me just go through solving this. So the first step in nodal analysis that we've talked about, and maybe I might be getting this a little bit wrong. It was a while since I did those nodal analysis videos, but one of the first steps is to identify the unknown nodal voltages, to essentially identify all the different nodes in the circuit, all the different places where you can have different voltages. So let's start out here. This is clearly one node. So everything that I'm shading in here all has the same voltage. So let's call that V1. Next, let's go ahead and say that all of this has the same voltage, clearly. Like there's just a wire connecting those two resistors, so that's all at the same voltage. Let's call that V2. And then we've got one more nodal voltage down here, kind of the node that runs along the bottom of the circuit. And we could call this V3, but remember one of the things that we have to do in nodal analysis is we have to set one of our nodes to be the ground node. So let's go ahead and set this to be the ground node. And there are a couple of good reasons for doing that. One reason is, you typically always set the ground node to be the node that runs along the bottom of the circuit. But another reason for doing this, for saying the ground node to be this bottom node here, and remember that means that we are going to define this ground node to be at a voltage of 0 volts. Okay, this blue node is going to be at a voltage of 0 volts. And one of the things that'll kind of help if we do that, if we define our ground node to be at a voltage of 0 volts, is that if all we care about is what is the voltage across this 13K resistor, essentially what is that voltage difference, then our answer for this problem is just going to be whatever the result is that we get for V2. Okay, so that's a good reason it might for like defining this to be our ground node as opposed to like this V1 node over here. If I said that V1 was my ground node, then I would have, my unknown voltage here, my unknown voltage here, and in order to get this final answer, I would have to subtract those two voltages. However, here I just have to know, whatever I get for V2, that's my answer to this problem. So anyway, that's, I guess, the first step. Just define all of my nodal voltages, or my unknown nodal voltages. The next thing we have to do is we have to assume current directions for all of our different elements. Clearly, we've got a current source here, so I'm going to assume that current is flowing in the same direction as the current source is actually pushing current. So we're flowing up here. For this 2K resistor, I am going to assume that current is flowing down. You can assume it really doesn't matter. You can assume current to be flowing any way, like either up or down through a resistor. It doesn't matter so long as you always say that current is going to flow from the higher voltage, the positive side of the voltage, to the negative side of the voltage, because that's what current is essentially doing. It's like saying, current flows from higher electrical pressure regions to lower electrical pressure regions. You can think about that just like, the wind outside. Wind is going to flow from areas of high pressure to areas of lower pressure. So anyway, let's assume that current flows down through that 2K. Current is going to flow to the right through that 5K. So this is our plus side, that's our minus side. And then current is going to flow down through that 13K. It's going to flow from plus to minus. So now we've labeled our unknown nodal voltages, and we've assumed current directions for all the different elements in the circuit. So now the next step that we have to go through is we have to write our, choose a different color, we have to write our KCl equations, which stands for our Kirchhoff current law equations. And remember, the important thing, or what you're essentially doing every time you write a KCl equation, is you are writing the sum of the currents that go into a node is equal to the sum of the currents that flow out of the node. Or, what the current that flows into a node has to equal what flows out of a node. And hopefully this is familiar to you. If what we've done so far in this circuit is unfamiliar, it might be a good idea to go and watch my other videos on nodal analysis. So anyway, now we've got two unknown nodal voltages. We've essentially got two equations here, or we've got two unknowns here, and therefore we're going to have to write two equations. So let's start out writing our first equation, equation 1. That's going to be the KCl equation for this particular node. So what flows into this node? Well, 10 milliamps flows in, right? And notice I'm asking what flows in directly to the node. Like you could argue, like, okay, well this current over here, eventually it's going to make its way back to V1. And also this current over here, like eventually it's going to make its way back to V1. And that's true, but we are looking for currents that flow directly into our V1 node. This 10 milliamp current source is the only current that's flowing directly into the V1 node. So what flows in is only 10 milliamps. And that is equal to what flows out of the node. So what flows out of the node, let's call this IA, let's call that IB, let's call this current IC. So what flows out of the node is my current IA, plus my current IB, plus my current IB. So now what we have to do, we've got essentially, now we've got, 5 unknowns in this problem. It seems like it's actually getting a little bit harder to solve. So now what we do, and hopefully this is review for you, hopefully you've seen this in the previous nodal analysis videos, is we're going to rewrite these currents using Ohm's Law. Remember, Ohm's Law says that voltage across a resistive element is equal to the current through that element times the resistance. So if I divide both sides of this by resistance, I get the voltage difference across a resistive element divided by the resistance of that element gives me the current through that element, right? And that's what we have here. We have current A, current B, and current C, IA, IB, and IC. So now, if I figure out what the voltage difference is across each of these elements, and I divide that by the resistance, that gives me the current, right? So let's see if we can use this to rewrite our current IA. So I've got 10 milliamps is equal to IA. So my voltage difference across IA is going to be the voltage on the plus side of my current IA minus the voltage on the minus side. So the voltage on the plus side is just V1. V1, the voltage on the minus side is my ground node, so it's just going to be 0 volts. So it's going to be V1 minus 0. And now I have to divide by the resistance. Divide by 2K. The next thing I'm going to have to do is I'm going to have to do the same thing for my current IB, okay? Because I've done that all for IA, so now I have to just do the same thing for IB. So for IB, I have got the voltage difference across this 5K resistor. On the plus side, I've got V1, and on the minus side, I've got V2. So the voltage difference here is going to be V1 minus V2, all of that divided by the resistance, which is 5K. So now that we've got that, let's go ahead and just sort of rewrite this. We're going to simplify this equation so that we can put it into a matrix really easily. Because we've got our two unknowns, which are V1 and V2, we want to pretty much separate out those unknowns, so this is going to be really easy to put into matrix form. So our new equation is going to be 10 milliamps is equal to V1 times 1 over 2K plus 1 over 5K. And then we're going to add that to V2 times minus 1 over 5K. I went through that kind of quickly. Hopefully you saw exactly how that works out. If I went through that too quickly, please go and rewatch some of my other videos. I explain kind of my method for simplifying this, which I think is pretty foolproof. Make sure that you're not missing any terms in this. So anyway, that is V1, and that's essentially my first equation. This is my first equation in a form that will go really nicely into a matrix. So now let's just go ahead and do the same thing for our second equation. So this is the second equation. And again, we just have to write what goes in equals what goes out. So what goes into my V2 node is my current IB right here. And the only thing that flows out is my current IC. IC flows out. So now, just like we did in this step, let's use Ohm's Law to rewrite our currents IB and IC. IB is easy. We actually already did this. IB is going to be V1 minus V2 over 5K, right? It's going to be V1 minus V2 divided by 5K. And then IC, the voltage difference, is going to be plus V2 minus 0 volts. So it's going to be V2 minus 0. And then we just have to divide by the resistance. Divide by 13K. So now what I'm going to do is I'm just going to rearrange this so we have all of our unknowns on the right-hand side. So I'm going to essentially subtract V1 minus V2 over 5K from both sides. And I'm going to end up with 0 is equal to, I could rewrite all of this, but I'm actually going to combine these steps, and I'm just going to separate everything out. I'm going to have V1 times minus 1 over 5K plus V2 times 1 over 5K plus 1 over 13K. And that is my second equation. So now I've got two equations, two unknowns, and now what I have to do is just basically solve this. This is now an algebra problem. So I am going to go ahead and pretty much use linear algebra. Let me just go ahead and put this into a matrix form. So this is going to be 1 over 2K plus 1 over 5K minus 1 over 5K minus 1 over 5K 1 over 5K, 1 over 5K plus 1 over 13K. This is my A matrix. My X matrix, or my X vector, it's a matrix too, but I call it, well anyway, it's really a vector. My X vector is going to be V1 and V2. And this is going to be equal to my B vector, which is, my B vector is 10 milliamps and 0. So really 10 milli, and 0. And then I pretty much just have to do A inverse times B to get my X vector. If any of what I just did is at all unclear to you, or I'm also about to solve this in MATLAB, if any of this is unclear to you, please go back and watch some of my earlier videos on all the linear algebra you would ever need in a circuits class. So anyway, this is now essentially a linear algebra problem. Any way you want to solve it is perfectly valid. I am going to solve this using MATLAB. So let me go, there's MATLAB. Okay. So let me just solve this using MATLAB, and actually I'm going to shrink my window down so you can see everything. There. Okay, so A is equal to 1 over 2K, which is 2e3, plus There we go. 1 over 5k, 5e3. Then we've got minus 1 over 5k. Then we go on to the next row, minus 1 over 5k, and 1 over 13k plus 1 over 5k. So I think that's everything we need for our A matrix. Let me just go ahead and put parentheses around those. I don't think I need the parentheses because of order of operations, but can't hurt. Anyway, that's my A matrix. Next thing I need is my B matrix. So my B matrix is 10 milli, so 10 E minus 3. That's how I would write 10 milli in MATLAB, and then 0. So that's my B matrix. And there are a number of different ways to compute A inverse times B in MATLAB. I could say, X is equal to A inverse times B. If you want to see kind of the complete catalog of how to do this in MATLAB, please watch my video. I have a video specifically on doing this in MATLAB. The way I'm going to solve this here is just A backslash B. And now I'm going to run this. And there, I guess it just ran. So now my X vector, V1 is equal to 18 volts, and V2 is equal to 13 volts. So let me just go ahead and pretty much copy those answers down that MATLAB just gave me. So based on what I just did in MATLAB, V1 is equal to 18 volts, and V2 is equal to 13 volts. So, and V2 is what we are looking for, so that's our answer. V2 is going to be equal to 13 volts. So let me just go up to this circuit and write V2 equals 13 volts. That's the answer that I got. So anyway, hopefully you found this helpful. And also, if you want to, it might be a good idea to simulate this circuit and just make sure that the simulation agrees with the work that we just did. Anyway, thanks so much for watching, and hopefully I'll see you in a future video. Thanks. Bye.